This is going to be a review of some of the mechanics, stuff that you should know from last year. There'll be some calculations that go along with this, but largely we're after the concepts. Except for this first part, we're going to do projectiles. You're going to need to know how to do a simple projectile calculation because we're going to make sure it comes up again and again. So as we get into that, here are kinematic equations. You've seen them before, you've used them, I hope you have them memorized, but I know better than that. So, these things tell me they relate changes in position to velocity, acceleration, and time. And the interesting things about these is that they are only useful when we have constant acceleration. But for projectiles, we always have constant acceleration. So, another thing to note is that anytime an object is in free fall, it's moving only under the influence of gravity. I'm going to slow down the writing there a little bit. So, anytime an object's in free fall, it moves only under the influence of gravity. That's the only force acting on it. Now, I know that in real life we have some air resistance and other things acting on objects, but when we talk about projectiles and things in free fall, we're going to go ahead and ignore that. It's an effect that overcomplicates things. We may talk in general about what that means, but when we're doing calculations, at least we're going to let that go. So projectiles are in free fall, meaning a projectile only has gravity acting on it. So the acceleration, at least on the Earth, of all projectiles is 9.8 meters per second squared down towards the center of the Earth. That's always a given piece of information that we have. Now, to make our lives easier, I like to round to 10 meters per second squared, because what's 2% between friends? So, the biggest thing for projectiles and two-dimensional motion is that, yes, motion can take place in 2 dimensions, but motion that's at 90 degrees to other motion, like let's say in the x and y dimensions, occurs independently and simultaneously. That means an object can move in the x direction and in the y direction, but anything that influences the x direction does not influence the y direction. They're completely independent of each other, but they take place in the same time. In most situations for how we do things, there is no acceleration in the x direction, and the acceleration is gravity in the y direction. 10 meters per second squared. It's in most situations where we're talking about projectile motion. That's not always the case. When we're in free fall, when we have a projectile, most situations there's no acceleration in the x, and the acceleration in the y is 10 meters per second squared down. So we're going to look at a quick example. We have a 5-meter tall cliff. We're going to fire a projectile going 4 meters per second. The projectile is fired at 4 meters per second horizontally. It's all in the x direction. How far does it go before it hits the ground? How far away will it hit? It will land. So the first thing we need to do always is to separate the problem into x and y columns. We need to separate our information into x stuff and y stuff. And then fill in our knowns. So we make an x column. In the x column, the acceleration is 0 because gravity only pulls down, and that's the only thing causing this object to accelerate. The initial velocity is 4 meters per second in the x direction. You can see that 4 meters per second is pointed in the x. That's all we know in the x. In the y direction, the acceleration is 10 meters per second squared down. Sometimes helpful to know which way positive and negative are. That's why we write the downs and the ups. The initial velocity in the y direction is 0. All of that 4 meters per second is directed in the x direction. And my delta y is 5 meters, and it's also down. We start off up, we end up down. So, Ultimately, we want to know how far away it lands. That's an x question. So our delta x is the initial velocity times the time. Problem is, I don't know the time, which means I'm going to have to go to the y direction to find that time. So we use a kinematic equation, delta y equals v0t plus 1/2 at squared. We pick this one because all four of our variables, acceleration, initial velocity, delta y, and time, are all in that equation, which means I can solve for the thing I don't know, which is time. So the v0t part goes away. Delta y is 1/2 at squared. We can easily solve for time here. Multiply by 2 on both sides, so the half goes away. Divide by a. And now we have t is equal to 2 delta y over a, but square rooted. So that makes the time come out to be 2 times 10 over 10. I apologize for that. It's 2 times 5 over 10. 2 times 5 over 10, which gives me 1 second. 2 times 5 over 10, which gives me 1 second. That's my time, but we're not done. We need our delta x. So that's going to be 1 second times 4 meters per second, or 4 meters. That's how we do projectile problem. That's how we do a horizontal projectile problem. That's kind of all I'm going to push you on right now. All right. Next thing that we're going to talk about is forces. Forces are important. We will always need forces. So to do forces, we've got to talk about Newton's laws of motion. He has 3 laws that tell us about forces. First law is that if there is no net force, there is no acceleration. All there is to it. You need a net force to have an acceleration. So if something is speeding up or slowing down, there must be a net force. If something is changing direction, there must be a net force. But if something is moving at a constant speed, or if something is sitting still, there's no net force acting on that object. No net force is no acceleration. The second law tells me that forces are the things that cause acceleration. If you have a net force, then you have an acceleration. In general, we write force equals mass times acceleration. But because it's talking about acceleration, I like to rewrite that as acceleration is force over mass. It lets me see how acceleration depends on force and how acceleration depends on mass. So, if the force goes up, the acceleration goes up. They are what we call directly proportional. If, however, the mass goes up, the acceleration goes down. That's indirectly proportional. Now, these first 2 laws describe what forces do to a single object or a single system. There's no interaction. They just tell me what happens to a single object in the presence of net force or in the absence of net force. The third law does more than that. So, one of the things that the third law says is that forces always occur in pairs between 2 separate objects. In order to have a force, you need to have 2 identifiable objects interacting with one another. We call that interaction force. So, if the action is that object A pulls on object B, the reaction is that object B pulls back on object A. That's my little formulation. If you can identify object A and B when we're talking about a force, then you can identify the action and the reaction. Now, an interesting thing about action and reaction, according to Mr. Newton, is that these third law force pairs, this isn't every pair of forces, it's just this specific object A pulls on B, object B pulls on A thing. Third law force pairs must always be equal in magnitude, that's size, and opposite in direction. I have to have that. Have to have that. Always equal in size, always opposite in direction. And this third law describes the interaction between two things, describes what forces are, the cause of every force, and the interaction between two objects. Or pairs of objects. And the last thing I want to bring up is a free body diagram. We did a bunch of these last year. We'll still do them this year. It's important. In a free body diagram, you have a picture of the forces acting on an object. When you draw a free body diagram, you need to be a little specific. For one, only forces go on the free body diagram. Two, they start at the point of origin and point in the direction of the force. Three, only forces go on the free body diagram and they must touch the object. Last thing, if you draw an acceleration, put it off to the side. It is helpful. Now, free body diagrams are useful in that they tell us, they lead to the second law. The second law says net force equals mass times acceleration. So my net force here is all my forces added together. All the forces with the acceleration are positive. All the forces against the acceleration are negative. So force 1 plus force 2 minus force 3 equals mass times acceleration. You're going to not know one of those things. Second law is going to help you find it. Last thing we have is energy. Now, last year, we really only talked about mechanical forms of energy. And by that I mean we talked about potential energy and kinetic energy. This year, we have kinetic energy. Kinetic energy was 1/2 mv squared. We're going to use a K for that from now on. That's the energy of motion. Anytime something is moving, it's going to have this kind of energy. The next thing we have is gravitational potential energy. This had to do with storing work against the force of gravity. For gravitational potential energy, we're going to use a U, and U is equal to mgh. Gravitational potential energy depends on height, depends on our position. The next thing we have is elastic potential energy. For this, you need something stretchy like a spring or rubber band. For this type of kinetic energy, for this type of potential energy, it's going to be 1/2 the coefficient of stretching, or what we call the spring constant, times how far we have stretched our spring quantity squared. These are what we talked about last year. We will add more. We're going to talk about different kinds of potential energy, electrical energy, heat energy, but this is going to do for now. We'll add them as we need to add them. Now, the biggest thing we did with energy last year was look at the conservation of energy. And this meant that for a closed system, the total energy of that system always remained the same. I can't get more energy in or out of the system. If I do work on that system, I can add energy, but that's putting energy in. As long as that system is closed, energy will neither be created nor will it be destroyed. So the energy at one point is equal to the energy at another point. That's any two different times or locations within a system. As long as that system is closed, the energy at one point is equal to the energy at another point. And that's our types of energy. The kinetic energy at one point plus the potential energy at one point equals the kinetic energy at another point plus the potential at another point. The amount of kinetic or the amount of potential may change, but the total, those two added together, always has to stay the same. That is our conservation of energy. That's a basic review of mechanics. We'll do a little bit of this with a lab coming up here. But that's what we need to know and be able to do.